Alright, so tonight we're going to take a look at the CLracing F7 board. We're also going to put it on a dual FC rig, and we're going to do some flight tests to compare the proposed matrix filter versus the existing dynamic notch. So buckle up, Dorothy. We're going to go for a ride. This board can take 2 to 8S voltage, has two ICM 2602 gyros in it, and has 32 meg of black box flash. We have a simple box here and the flight controller inside, of course. Let's pull that out. We get accessories with it, of course, as well. Take this off. In the bottom here, we have the standard ribbon cable, and then we have another connector here and a bunch of gummies. Looks like we get 6 gummies, which is kind of nice. A couple of connectors there as well. And then this is our 4-in-1 ESC connector, which obviously would plug right into here and then down to our 4-in-1 ESC. Taking a look at the specs on this, I have the dual V2 variant of this board. You can also get it with an MPU 6000 gyro instead of the ICM 2602 gyros here. And that in that configuration would just be a single, not a dual. They're actually up to version 2.1 now, which I'll show you that in a little bit. About 36 bucks for the 2.1 version, the latest version, so it's a pretty good deal for an F7 board. We're running at a 260 megahertz processor speed. Some of the things that I've underlined here are what make this board a little special. This has a 2 to 8S VBAT it can accept. Has a 3 amp BEC on it for 5 volts. You can power or turn off your VTX completely, like not pit mode, actually turn it off within this board on a switch. Has camera control, but this is the resistor type. Obviously, you can also just power your multiple cameras nowadays right through the UARTs for camera control as well. So this you can do either one. Of course, we have up to 6 UARTs, so you got plenty of UARTs here. There's some nice buzzer pads at an appropriate spacing. So you can take your piezo buzzer and put it right onto the board. It's really nice. We'll show you that here in a second. VBAT has some polarity protection on this, and then 32 meg of onboard flash for black box logging. The layout on this board makes a lot of sense. At the front here we have our camera connectors here and also our connectors for our receiver, whether TBS or any other kind of receiver. At the back you have your USB on the side here, so that's easily accessible, and here's the actual board itself. On the left hand side here we have a bunch of UARTs, and this is our buzzer connection. So the spacing of these pads completely lines up with a piezo buzzer, so you can just take the buzzer, bring it up to here, maybe snip a little bit off so you just have a little bit of stub here, and just solder it right to this spot, and it would just, and obviously just hang off the edge here. But it's on the size of the quad, so it's, it's going to be plenty loud, and it's not going to be interfering with anything. On the back of the board here we have our connections to our VTX, which again you can turn on and off with this board. We have our jumper pads here to solder, so you would solder this for 5 volt to your VTX, or if you want VBAT to your VTX, you'd solder these two. Here again, this is how you can activate pit mode or on and off with the VTX. With this jumper, you're going to either choose that the connector for the motor outputs is going to be motor 4 or LED, and then also we can connect GPS right here into these pads. It's kind of oriented for that. In the back here we also have some additional pads for hooking up LEDs off to the back of the quad or out to the arms or whatever. On the underside of the board we essentially have the same pads here that we have on the other, so depending on which way you orient this on the board, you're going to have access to these pads to solder on the top in either direction. So you can have it oriented this way, orient this way, and obviously you can have access to these pads for wiring up your camera, your receiver, your buzzer, some UARTs, and then your VTX right down here. This is obviously the pin header to go to your 4-in-1 ESC. As I mentioned before, the latest version of this board is the V2.1. Essentially the board is the same thing, which you can tell just by graphically looking at the board if it's different, is if it has this little notch out over here in the layout, so the board actually dips down. The pads are basically the same layout. Some minor differences, you can check those out. I don't have, again, that 2.1 board. I have the 2.0 right here. One big difference on the 2.0 board that you get is it has direct capability to power the CLracing Bluetooth module. If you have the Bluetooth module with the version 2.0 board, you have to have an external power source wired to the Bluetooth module itself, which obviously you would plug in to the USB here, and then you can use the SpeedyBee app to program this with Betaflight or whatnot. With the 2.1 board, it will power this SpeedyB module directly from the USB, and you wouldn't need any external power to power this when you plug it into the USB. So you just take this chip, it's about 16 bucks, plug it in, and then you can connect to the SpeedyB app. There's only 2 boards on the market that do this with the powering. One is the Power Drone board, and then also the CLracing F7 board. Okay, so that is the general rundown on the CLracing F7. What we're going to do is we're going to flash this up to Betaflight 4.2, and we're going to do some comparisons of the matrix filter versus the dynamic notch with a variant build of Betaflight with the matrix filter, and then obviously just the stock Master 2.0. We're going to take the CLracing F7 here, and we're going to mount it into my dual flight controller rig here. This is the SPracing F7, and then we're going to put the CLracing F7 up top here, and we're going to be able to see the difference between those filter performance and also the difference and see how well the CLracing F7 is doing with its gyro reads versus the SPracing F7, which we already know does pretty well. This is the matrix filter versus the dynamic notch. Alright, so let's take a look at this flight. Now on this is the SPracing F7 making this flight. The CLracing F7 is on board for the ride. So you can see right here, the 2 boards are in there, and the CLracing F7 is at the top and the SP is at the bottom. So I'm just going out to do a bunch of moves, and I'm really trying to get a bunch of different high throttle values and flips and rolls, and really put the notch filters to the test of moving them around, giving them a lot of different frequencies. Some people ask sometimes, you know, can you upload a kind of a quad that's not tuned? Or a lot of the stuff they're seeing is, I guess they think it's fairly well tuned. I don't think it's that great, but this quad is not tuned. You can see right there, see the throttles. So the P term needs to be a little bit more on pitch. You can see a decent amount of wash. This has the D gains for D-min down in the 30s. They should really be starting in the 40s for this. This is about a 650 gram all up with the battery, GoPro in the front, so it's pretty heavy. Smooth forward flight's pretty good here. Flips and rolls, I don't really see any bounce back, but the throttles is something that this definitely has, and the prop wash is, yeah, it's okay, but it's not great. Just doing a couple of twitch moves, almost plants it right there. And again, some more stepped and smooth forward flights, and then some stepped throttle punch. I guess I didn't do that there. Some prop wash turns. What we'll do here is both of these are grabbing logs then in this flight. So we got the logging on the bottom and on the top. And we're gonna, right after this, compare those two and see what we see which performs better. Little inverted yaw, a little hard when it's dark. It's kind of dark out, the cameras might not show it too well. It's kind of hard to get the orientation there. It's mostly just black, looking straight down. Yeah, that's the extent of it, so let's check out the logs, see what we find. So what is the matrix filter? Well, the matrix filter is proposed by Pavel. He has a YouTube channel, which I'm sure you're already aware, but I'll put a link down in the description. He's an iNav developer. The matrix filter is currently in iNav, and essentially it is a variant of the dynamic notch. The dynamic notch currently works that independent on each axis, so you have the roll axis, the pitch, and the yaw. The notch filter tracks peak frequencies, targets those, and moves to those. So it's doing that for the roll, independently of the pitch, independently of the yaw. What Pavel's done is basically the same thing, but then he puts a notch filter on each axis from where the notch is on the other axes. So the roll will have a notch filter where the roll axis is detecting peak noise, but it will also put a secondary one for where the peak noise is coming from pitch and from yaw. So there'll be 3 notches on each axis, and they're going to all move around based on where the peak noise is on the other axes. The dynamic notch classically doesn't work like that, so it's just a little bit of a variant on it, and see if it performs better. This is how this stuff works in pull requests for any of the firmwares. People will code something up, propose it, People take a look at it, see how it performs, conversations will start, and if the proposal is a good one, gets vetted, the code gets checked, seems to show value, then it will get merged in to the master for the project, and now it's in the project. So if you're interested in doing testing for either Betaflight, iNav, or anything else, just go to the GitHub for any of the projects, go to pull requests, and you can see a whole list of them right here. So you can see this is all the current pull requests of people coding things up to put into Betaflight. Some are more involved than others, some are little fixes, some are big whole new features. And you can kind of look by the tags to see what things are from a high level standpoint. For the matrix, we just type in matrix here. That gives us that keyword. And eventually you may do that in the future, depending on what you're watching this video. Maybe it's already been merged, or maybe it's got rejected if we find issues with it or there's not that much value. So what we're doing with the CLracing F7 board and SPRacing F7 board, putting those on the same thing, running the classic dynamic notch on one of them and the matrix filter on the other one. It's the same flight, same noise, same everything. So let's see what we get. Now, to compare two logs like that, there's a great tool developed by Brian White, and he's very active in the logging Facebook group, which I'll put a link for that down below as well. And this tool is called PID Toolbox. You can load up two different logs, so maybe it's just two different flights. It doesn't have to be the same flight. And you're comparing, when I made settings changes, did it actually improve things? I have a video on this, make a link to that down below as well, but do check it out. So you can see the logs here, almost the exact same length down to 1 second off. And that's just probably a rounding thing or whatnot. You can see the throttle positions between the two. So this is roll, pitch, yaw on the CLracing F7. This is SPRacing F7, roll, pitch, yaw here. And you can see the throttle positions and how it's really the same thing because it's the same flight. And it's just both boards are recording the gyro and just running different filter setups on that gyro signal. Obviously, the CLracing F7 is not flying it, so that the PID loop's doing its thing on the CLracing F7 and spitting out some motor commands, but those aren't doing anything. Whereas the SPRacing is doing the same thing. The PID loop's running and spitting out motor commands, and that's what's actually changing the motors. So we can do a spectrum analysis on the two different logs to see which perform better. Conversely, we can see through this if the CLracing F7 board is doing a good job, just general performance. I already know the SPRacing F7 performs well, but is the CLracing F7 doing a good job as well? Pair the two, we're going to go in the spectrum analyzer. Then we're going to go pick gyro A for log A and gyro B for log B. I can also do the D term here, but I did notice in the one log I had the D-min gain different than the other, so we're not going to look too much at the D term, but normally I would, so I'll do it here again. So we'll do D term A and D term B, and it's just very helpful when you're looking at noise because the D term is what really amplifies the noise. So a lot of times I'll look at the filter gyro and the D term, and they kind of show the same thing, but the D term ultimately shows what's being amplified the most and being pushed out to the motors in a lot of cases. After you pick those, you go ahead and hit run. And after it runs all the spectrographs, you can see the waterfall graphs here. What this shows is the full range of throttle, so 0 to 100% throttle. So as I'm moving throttle, and then it shows the hertz, the speed of the oscillations that you're seeing. So 1,000 hertz is more than 800 hertz, which is more than 200 hertz. And what that really means is it's an oscillation at 200 times a second, 800 times a second, or 1,000 times a second. And obviously you can see as the throttle increases, the range of noise from the motor band, the vibrations increase in speed. What we can do here is change the scaling a little bit. So we can do that to 0.25 just to change the intensity of the magnitude there. So you can see that brightens that up a little bit. And then here we can set this to 1 to dim down the D term just a bit. The brighter whites are higher magnitude, so the vibration is higher in amplitude. When it's darker, that means the vibration is lower in amplitude. So you can see here, this is the SPRacing F7 with what we'll call the classic dynamic notch, and then this is the proposed matrix filter. The other thing I did on this is I tried to get the latency about the same, so I changed the Q factor of the classic dynamic notch to 165, and the Q over here was 180, so there's more notches, right? There's 3 per axis, and there's in the classic there's 2. They shoulder each other, so In this, there's 2, and this, there's 3. So this is at the Q of 250, this is at a Q of 165, and that's about, using my spreadsheets, about the same latency. So we have kind of an apples to apples, unless I did anything wrong in this test, which obviously I uploaded this stuff so somebody can review it and tell me if I screwed something up. But anyways, so about the same latency, about the same filtering. Obviously the filter sliders are the same, the PIDs are the same for all this. I just messed up that one D-min gain thing. So that's has an impact over here, but won't have an impact on these graphs. Ultimately, you can see the classic dynamic notch still is letting through a little bit of motor peak band where the matrix filter is not. It looks like it's doing a pretty good job. So good job, Pavel. It appears like you might be onto something here. So of course, what you do when you're looking at stuff for PRs, you go ahead and upload your results. So I'm putting on a spectrogram here, a little info on what I did, and then obviously the logs here. It's a zip file, has both of the logs so people can download it and look for themselves. And that's how we go through firmware development. So anyways, that's how it works. If you're interested in doing any testing for the Betaflight or iNav projects, check out PRs and see what browses and suits your fancy. We can also see that the CLracing F7 did a good job at its gyro, so there's no issues with the gyro or electrical noise or anything causing issues on the CLracing F7. So it's a good board, good layout. Definitely check out the CLracing F7 board for 35 bucks. Pretty good cost for that. And also, if you're interested in keeping track and following along with how this matrix filter evolves, you can check out this PR, again, link down below, and I'm sure there'll be other data and so on and so forth. The next thing I want to do that probably won't make a video about it is I want to compare the matrix filter versus the RPM filter, because the RPM filter then has 4 notches per axis and it follows each motor, whereas Pavel's thing is following the peak on each axis and then replicating notches on the other axes for all those different peaks. Hence the matrix, because it's 3, 3, and 3. I'll put a link down in the description. He has a video all about the matrix filter. Check that out. Okay, everybody, that's it. Hopefully a feature-packed video. We got a review, matrix filter flight testing, and talking about just tuning and whatnot. Thanks again, and I hope this helped.